Alright, let's go. Number 8. The photograph. In April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, but not the one at the center of our galaxy. They chose M87, 53 million light-years away, because it was an easier target than the supermassive black hole sitting in our own backyard. Our closest one, Sagittarius A*, was the harder problem. Its image would take 3 more years to arrive, and the delay was not because the telescopes were slow. The delay was because Sagittarius A* refused to sit still long enough to be photographed. Standard theory says a black hole should cast a shadow, a dark central region where photons cannot escape, ringed by a bright halo of accretion disk material, bent into a near-perfect circle. The Kerr geometry predicts the shadow's diameter to within a few percent for a given mass. Radio photons at 1.3 millimeters should trace the ring cleanly, because at that wavelength interstellar dust becomes transparent. Once resolution was high enough, the image had to exist. The mathematics left no room for surprise. On May 12, 2022, they got it. A dark disk surrounded by a lopsided orange ring, about 52 micro-arcseconds across, sitting exactly where the mathematics said it would. Shepard Doleman of the Center for Astrophysics at Harvard led the collaboration. The results were published across 6 papers in a special issue of the Astrophysical journal Letters on the same day the image was released. 8 radio observatories, spread from Hawaii to Antarctica to Spain to Mexico, had been synchronized for a single week in April 2017 to work as a single virtual instrument, roughly the diameter of the entire planet. Getting the image took 5 years of computation. Sagittarius A* varies on timescales of minutes. M87's black hole varies on timescales of days, giving observers a much steadier target. Interstellar gas between Earth and the galactic center scatters the incoming radio signal, blurring the picture. Coverage of the visibility plane was sparse, meaning many possible images could technically fit the data. Different reconstruction algorithms produced somewhat different reconstructions, and the collaboration had to average across multiple methods to publish a single result. In 2022, a group led by Makoto Miyoshi at the National Astronomical Observatory of Japan reanalyzed the exact same 2017 dataset and argued that the ring structure itself might be an artifact of the imaging pipeline, that the true underlying source could be more elongated or asymmetric than the released image suggests. The EHT collaboration has published counter-arguments. The debate is not fully resolved. Follow-up polarization images released by the EHT in 2024 confirmed strong ordered magnetic fields around the shadow, adding independent evidence for the black hole interpretation, but did nothing to close the internal disagreement about the exact ring geometry. The picture everyone circulated is a composite, and the arguments about its finer structure have never fully died down. You are now living in the first generation of humans that has actually seen the object your entire galaxy is bound to. A photograph exists. It matches an equation Einstein wrote in 1915 with disturbing precision. The thing at the center of your night sky has a face, and we finally know roughly what it looks like, even if we still argue about the edges of it. But the darkness inside that ring, what is it made of, if anything, and does our physics survive whatever sits behind it? That was the outer shell of the mystery. The inside is stranger. Number 7. The Ancient Stars. In 2015, astronomer Louise Howes and colleagues at the Australian National University were surveying the Milky Way's central bulge with the SkyMapper telescope in New South Wales. They were hunting for extremely metal-poor stars, stars so lacking in heavy elements that they must have formed within a few 100 million years of the Big Bang. The team's expectation was that most surviving ancient stars would be sparse and scattered through the outer galaxy, and that the crowded, chemically saturated bulge would contain almost none. Textbook Galactic Evolution says the earliest stars should live in the halo, the sparse outer sphere of the Milky Way, because the halo collapsed first, before the disk had time to settle out of the collapsing gas. The dense central bulge, saturated with supernova explosions and chemically polluted by 10 billion years of stellar death, should be dominated by younger, metal-rich populations. Ancient stars should not survive there, and if any do, they should not stay long. That is what every simulation had said for decades. They found the ancient stars in the wrong place, deep inside the bulge, some with iron abundances less than 1/10,000th of the Sun's, sitting in the galaxy's most chemically polluted neighborhood, right next door to Sagittarius A*. Howes, Karen Lind, Martin Asplund, and collaborators published in Nature in November 2015. The paper reported the discovery of extremely metal-poor stars in the bulge, including a subset confirmed with high-resolution follow-up spectroscopy on the Magellan telescopes. Several stars showed iron abundances low enough that they are candidate descendants of the very first stellar generations, some possibly formed within the first billion years of cosmic history, when the universe itself was still assembling its first galaxies. Explanation 1. These stars formed in the outer halo and migrated inward through gravitational scattering over billions of years. Their measured orbits stay tightly bound to the bulge, showing no signature of recent infall from outside, and no plausible scattering mechanism has been shown to move enough of them inward in the observed time. Explanation 2. The galactic center itself formed first, seeding old stars in place, which reverses the standard textbook order of Milky Way assembly and requires rewriting how the earliest baryonic structure collapsed inside the dark matter halo. Explanation 3. They were captured from earlier dwarf galaxies that merged with the young Milky Way in the first few billion years after the Big Bang. Their kinematics don't cleanly match any known merger stream, and the metallicity distribution of the captured population would have to be finely tuned. Explanation 4. They are chemically unusual young stars masquerading as old ones through some rare stellar atmosphere process. Their carbon to iron and magnesium to iron ratios argue against that reading. Follow-up surveys with the European PIGS program, Pristine Intergalaxy Survey, have found dozens more candidates over the past few years, but have not resolved the underlying question of how they got there, or which of these four scenarios is closest to right. If ancient stars really did form at the galactic center first, our galaxy's growth history runs inside out. The narrative you learned in school, that structure builds slowly from the outer regions inward, flips. The most radiation-hostile neighborhood in the Milky Way today may be the same neighborhood that lit up before anywhere else did, 13 billion years ago. What conditions birthed the galaxy's first stars in a region where our current physics of star formation shouldn't have permitted it? Even those stars are dwarfed by the structures we found next. Number 6. The filaments. Farhad Yousefzadeh, a doctoral student at Columbia University in 1984, was mapping radio emissions from the galactic center with the Very Large Array in New Mexico. His thesis project centered on understanding the diffuse plasma physics of that region. He assumed his data would show shells from old supernova remnants and diffuse blobs of ionized gas around hot young stars, because that is what radio surveys almost always show. Then his images returned something no astronomer had ever asked for, and no theorist had predicted. Radio structures on galactic center scales tend to come in two categories: roughly spherical supernova shells expanding into the surrounding medium, or amorphous emission around HII regions where young massive stars ionize the gas around them. Astronomy in 1984 had never mapped a natural radio source that organized itself into long, straight lines of any kind. There was no theoretical framework predicting anything like straight lines at all, and no comparable structures had ever been observed anywhere else in the universe. He found needles, some over 150 light-years long, some less than a light-year wide, perpendicular to the galactic plane, perfectly straight, some arranged in parallel groups, as though something had combed them. Yousefzadeh, Mark Morris, and Don Chance published the discovery in Nature in 1984 under the title Large, Highly Organized Radio Structures Near the Galactic Center. Over the next 3 decades, follow-up surveys with better instruments slowly identified roughly 200 filaments in the region. Then in 2022, Ian Haywood, Yousefzadeh, and collaborators, using new observations from the Meerkat Radio Array in South Africa, published a catalog containing nearly 1,000 of them, a 5-fold increase in less than a year of dedicated observing time. Explanation 1. Relativistic electrons spiraling along magnetic field lines produce the observed synchrotron radio emission. The spectrum fits, but the model says nothing about why the field lines are so ordered, so long, and confined only to the galactic center. No comparable filaments have been convincingly detected around any other galactic nucleus in the local universe. Explanation 2. relic jets from past outbursts of Sagittarius A asterisk. The filaments are not aligned with any known jet axis of the black hole, and their orientations differ from one filament to another, which is not how jets behave anywhere else. Explanation 3. Cosmic string signatures, the geometrical remnants of phase transitions in the very early universe, considered decades ago. No independent evidence has surfaced in any other astrophysical dataset since. Explanation 4. Interactions between fast-moving molecular clouds and the ambient magnetic field of the central region, a mechanism proposed by Yousefzadeh himself in later papers. Partial fit leaves the length distribution and the parallel groupings unexplained. Explanation 5. Added after the 2022 Meerkat catalog. Statistical patterns in the filament population suggest they may be linked to activity from an intermediate mass black hole population near Sagittarius A asterisk, but no direct source has been identified for any individual filament. 40 years after the initial discovery, there is no consensus on their origin among the astronomers who have spent entire careers on them. There are almost 1,000 of these needles across the volume of your galaxy's core, and no working physicist can tell you what draws them there. Something at the center of the Milky Way is generating parallel lightning rod structures on scales that dwarf every human construction combined, and doing it invisibly, without leaving a signature at any other wavelength. What organizing principle at the galactic center produces 1,000 parallel needles, 150 light-years long? The filaments at least sit still. The next mystery flickers. Number 5. The flares. In September 2000, Frederick Baganoff and colleagues at MIT began using the newly launched Chandra X Ray Observatory to establish a long baseline monitoring campaign of Sagittarius A asterisk. Given the black hole's relatively low quiescent luminosity, orders of magnitude fainter than a typical active galactic nucleus, the community expected a quiet source. The plan was to characterize a baseline over months of unremarkable observations, then use that baseline as a reference for future studies of other galactic center sources. A supermassive black hole, feeding on ambient gas, should emit relatively steadily. Accretion disk luminosity should vary on timescales of days to years, tied to the viscous timescale of matter spiraling inward through the disk. Rapid, dramatic brightness spikes on human timescales, minutes, hours, are not a natural output of standard accretion theory for a source this size. The mathematics of thin disk models does not readily produce them. On October 27, 2000, they caught one. Sagittarius A asterisk brightened by a factor of 45 in X-rays within 3 hours. Then, just as suddenly, faded back to baseline. Baganoff, Bouts, Brandt, Cui, Doty, Feigelson, Garmier, Pravdo, Ricker, and Townsley published the result in Nature in September 2001, titled Rapid X-ray Flaring from the Direction of the Supermassive Black Hole at the Galactic Center. Since that first flare, hundreds have been recorded across X-ray, infrared, and radio wavelengths. In May 2019, Tuan Do and colleagues at UCLA, using the Keck telescope on Mauna Kea, observed Sagittarius A asterisk brighten in near-infrared by a factor of 75 within 2 hours, the brightest event ever recorded from the object, so extreme that Do's team initially wondered if the calibration was wrong. Explanation 1. Gas clumps periodically falling inward from the surrounding accretion flow, each clump producing a single burst as it heats and radiates. The required geometries and infall masses don't reliably reproduce observed flare statistics across the full wavelength range, and the predicted delays between X-ray and infrared peaks don't match the data cleanly. Explanation 2. Magnetic reconnection events in the accretion flow, analogous to solar flares scaled up to a supermassive black hole's magnetosphere. This is the leading model in most modern papers, but it does not fully explain the flare timing distribution or the observed multi-wavelength correlation between X-ray, near-infrared, and sub-millimeter flares. Explanation 3. Bright hot spots orbiting near the innermost stable circular orbit, whose motion produces the flare signature as they sweep past our line of sight. Gravity collaboration infrared observations in October 2018 detected exactly this kind of orbital motion during a flare, an astonishingly direct measurement of matter moving at close to a third of the speed of light near a black hole, but not every subsequent flare has shown similar signatures. Explanation 4. A swarm of small compact bodies, periodically tidally shredded by the black hole. Speculative, no direct evidence, and the required population of small bodies would need to be replenished continuously. 25 years of monitoring, no unified model of what actually powers these events. At any moment, without warning, the object your galaxy orbits can double, triple, or quintuple its output for reasons no observer on Earth can predict in advance. Every large flare has arrived as a surprise. Nothing in our current theory tells us when the next event 10 times larger than 2019's will happen, or why, or whether there is an upper limit at all. What if a flare 1,000 times larger than any we have yet seen occurred tomorrow? Would we have any warning at all? The unpredictability grows more uncomfortable when a specific star is the test. Number 4. The star that outran Newton. In the early 1990s, 2 independent teams began the tedious work of tracking individual stars near Sagittarius A** year after year, star by star, night by night. Andrea Ghez at UCLA used the Keck telescope on Mauna Kea. Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics used the European Very Large Telescope in Chile. Both groups were measuring stellar motions to weigh whatever invisible mass was sitting at the exact dynamical center of the galaxy. The work was slow, unglamorous, and demanded a decade of patience before any single stellar orbit could be closed. Newtonian gravity predicts stellar orbits are perfect closed ellipses that repeat indefinitely. General relativity predicts that in strong gravity, those ellipses precess. The whole orbit rotates slightly with each pass, tracing a rosette pattern rather than a fixed ellipse. Mercury, orbiting our Sun, precesses by only 43 arcseconds per century, and that measurement helped confirm Einstein's theory a century ago. Around a supermassive black hole 4 million times the Sun's mass, the same effect on a nearby star should be enormously larger and directly measurable within a single orbit. In 2018, the star S2 made its closest approach to Sagittarius A* in 16 years. It passed within about 120 astronomical units of the black hole. Its speed at closest approach reached 7,700 kilometers per second, roughly 2.7% the speed of light. Its orbit precessed exactly as Einstein said it would. Genzel's gravity collaboration published the result in Astronomy and Astrophysics in April 2020, quantifying the Schwarzschild precession of S2 at approximately 12 arc-minutes per orbit, matching general relativity to within measurement uncertainty. Ghez and Genzel shared the 2020 Nobel Prize in Physics for the decades of stellar tracking that led to this and related results, work that began before either of them had a permanent academic position and required them to defend the project against skeptical review committees for years. Newer analyses have quietly complicated the clean picture. Several independent studies suggest small residual anomalies in S2's motion after all known relativistic effects are subtracted from the data. Deviations at the level of a few percent of the predicted precession, small enough to be dismissed as noise, large enough that no serious group ignores them. Explanation 1. Additional dark mass distributed near Sagittarius A*, possibly the outer edge of the swarm of small black holes described later on this list, gravitationally perturbing S2's path. Explanation 2. An intermediate mass companion black hole hidden within the innermost region, weighing perhaps a few thousand solar masses, an object nobody has directly detected, but whose gravity would explain some of the residuals. Explanation 3. Sagittarius A** spins faster than early models assumed, adding a lens-thurring frame-dragging correction that has not yet been fully measured or subtracted from the data. Explanation 4. Subtle measurement systematics that will vanish once the next decade of gravity plus and extremely large telescope data come in. Each proposed correction fits some subset of the observations and misfits another. The cleanest strong field test in gravitational physics still is not quite clean, and the size of the anomaly is exactly the size that would matter if any of the exotic explanations turned out to be right. A star spinning around your galactic center at nearly 3% of light speed is the sharpest current evidence that a real black hole, and not merely something acting like one, sits 4 million times heavier than the Sun at that same spot. Its motion is the closest measurement we have to touching that object. If those small orbital anomalies are not measurement error, what invisible mass is nudging S2, and why haven't we yet seen it? That was an object we can see. The next mystery survived by hiding. Number 3. The cloud that should have died. In 2011, Stefan Gillissen and colleagues at the Max Planck Institute for Extraterrestrial Physics were tracking objects near Sagittarius A** with the Very Large Telescope in Chile when they identified something unusual on their infrared images. A diffuse, dust-shrouded blob was on a nearly radial plunge toward the black hole. They calculated its trajectory carefully. Its orbit was so extreme that it would reach closest approach in the middle of 2014, and every model they ran said it would not survive the encounter. A loose gas cloud plunging within a few hundred astronomical units of a supermassive black hole should be torn apart by tidal forces. Its material should be stretched into a filament, ionized, and steadily consumed by the accretion flow already present around the hole. Astronomers around the world prepared for a brilliant months-long accretion flare, a real-time feeding event captured across every wavelength of every major telescope humans had built. Some observers cleared their observing schedules for years in anticipation. G2 made its closest approach in 2014. It came within roughly 200 astronomical units of Sagittarius A*, and then essentially nothing. No flare, no dramatic spike. The cloud emerged largely intact and continued on its outward leg. Gillissen, Genzel, Fritz, Quadart, and collaborators published the discovery and prediction in Nature in January 2012. Follow-up analyses by Andrea Gheze's team at UCLA, published in the Astrophysical Journal in 2015 and again in 2020, tracked the object after periastron and found it emerged with *its overall shape and orbit largely unchanged from the pre-encounter model. The expected feeding event never happened, and the total energy released by Sagittarius A* over that period was consistent with its normal quiescent output. Explanation 1. G2 contains a hidden central star whose gravity holds the surrounding gas together against the black hole's tidal forces. Plausible, and now the leading hypothesis in most published models, but no direct detection of the central star has been confirmed to everyone's satisfaction. The object is small enough and dust-shrouded enough that the star, if it exists, hides inside its own envelope. Explanation 2. G2 formed from the recent merger of two binary stars, producing a bloated stellar remnant, with dust wrapped around it. The scenario gives the object stellar cohesion, but has trouble matching the observed extended geometry of the surrounding gas both before and after periastron. Explanation 3. G2 belongs to a class of similar objects, sometimes called G objects, or dusty object stars, that populate the region near Sagittarius A* in numbers larger than anyone had realized. Andrea Gheze's team has since identified at least 6 similar objects in the same region, suggesting the phenomenon is common rather than one-off. Explanation 4. Our theoretical models of how quickly gas can actually be absorbed by Sagittarius A* are systematically wrong, meaning the standard picture of low luminosity accretion around our black hole is missing a significant piece of physics. Uncomfortable, because it would force revision of the textbook chapters describing how supermassive black holes feed. A decade later, no consensus among the groups who have modeled the encounter in most detail. Something orbited within spitting distance of a 4 million solar mass black hole and emerged mostly unhurt. Either that object is far more solid than it appears from the outside, or the deadliest region in your galaxy is measurably less deadly than physics said it had to be. Both possibilities revise something you thought you understood about how the universe works close to gravity's extremes. How many other compact objects are hiding inside apparently empty gas clouds near Sagittarius A*, waiting for their own close approach to reveal them? The next entry pushes the hidden count much higher. Number 2. The Hidden Swarm. In 2018, astronomer Chuck Haley at Columbia University sat down with 12 years of archived Chandra X ray observatory data covering the innermost 3 light-years around Sagittarius A*. He was not hunting for a swarm. He was studying quiescent X-ray binaries, faint stellar systems, where a compact object slowly draws material from a companion star, producing a distinctive low-luminosity X-ray signature. His question was mundane, aimed at understanding the statistics of ordinary binary stars in extreme environments. The answer was not mundane at all. Theoretical predictions dating back to the 1970s had suggested that stellar mass black holes across the Milky Way should slowly sink toward the galactic center through a process called dynamical friction. Heavy objects gradually settle into denser regions over billions of years, transferring their orbital energy to lighter stars around them. Estimates from various theorists said that thousands of stellar mass black holes, the remnants of the most massive stars ever born in the galaxy, should by now be piled up inside the central parsec. Nobody had ever directly observed a single one there. It was a prediction waiting for evidence. Halley's team found 12 X-ray sources, with signatures consistent with stellar mass black holes, drawing gas from companion stars. All 12 were clustered tightly within 3 light-years of Sagittarius A*. The 40-year-old prediction had suddenly become a measurement. Halley, Kaya Mori, Franz Bauer, Michael Berkowitz, Yazub Hong, and Benjamin Horde published the result in Nature in April 2018. The team argued that these 12 visible binaries represent only the small fraction of the true population that happens to be currently accreting brightly enough to detect with Chandra, implying a total of roughly 10,000 or more stellar mass black holes packed inside that same central parsec, the vast majority of them invisible to any current instrument on Earth or in orbit. Explanation 1. The 12 sources are not stellar mass black holes at all, but instead millisecond pulsars in binaries. Their X-ray spectra don't cleanly match known pulsar populations, but the debate continues in the literature. Explanation 2. The objects formed in place from massive stars born near the galactic center, rather than migrating in from elsewhere in the galaxy. Some independent stellar population modeling supports this local formation route. Explanation 3. The swarm was seeded by the tidal disruption of ancient globular clusters that fell into the center over cosmic time, partial support from separate N-body simulations of Milky Way assembly. Whichever formation channel actually dominates, the underlying conclusion has not been dislodged. The galactic core hosts thousands of black holes we cannot directly see. If Halley's estimate holds, the volume within 3 light-years of the galactic center contains more black holes than we have identified in the entire rest of the Milky Way combined. Your galaxy has a densely populated graveyard at its heart, and every one of those graves has enough mass to warp spacetime measurably around itself. How many of those thousands of hidden black holes are drifting on paths that will eventually spiral into each other, sending gravitational waves through everything, including you? Every mystery on this list orbits the same object. That object is number 1. Number 1, Sagittarius A* itself. In February 1974, radio astronomers Bruce Ballack and Robert Brown, working at the National Radio Astronomy Observatory in Green Bank, West Virginia, were using the Green Bank interferometer to map compact radio sources in the direction of the galactic center. They were surveying, following up on hints from earlier observations that something bright and compact might sit near the galactic middle. When they combined their interferometric data, a single sharp point emerged from the noise at the exact dynamical center of the galaxy, brighter, smaller, and stranger than anything anyone had predicted. Standard stellar dynamics said the mass at the center of a galaxy should be smoothly distributed, concentrated toward the middle, but continuous. Plot orbital velocity against radius, and you should get a smooth curve, without any sharp features. There was no theoretical requirement, at the time of the discovery, for a single dominant object weighing millions of solar masses to sit at the exact center of any galaxy. Supermassive black holes were still a hypothesis without a confirmed example anywhere in the universe. They found one anyway. Astonishingly compact, extraordinarily bright in radio waves, positioned at the exact dynamical center of the galaxy. It had no visible counterpart in any other wavelength than available to observers. Ballack and Brown reported the detection in the Astrophysical Journal in December 1974. The name Sagittarius A*, with the asterisk, was coined by Brown in a 1982 paper, chosen because the source was so exciting it deserved a distinct designation, similar to the way excited atomic states are marked. By 2002, careful tracking of individual stellar orbits by Genzel's team confirmed the enclosed mass within roughly 100 astronomical units of that exact point was approximately 4.1 million solar masses. No known kind of object of that mass could occupy that little volume except one. Explanations attempted over 5 decades. A dense cluster of neutron stars packed tightly enough to look point-like from Earth. Ruled out, such a cluster would collapse under its own gravity within about 100 million years, which is far shorter than the age of the galaxy. A cluster of some other kind of dark stellar remnant, packed even more tightly, of the sort that some 1970s and 1980s theoretical papers proposed as an alternative to a central black hole. Same underlying collapse problem, in every viable variation of the model. A boson star made of hypothetical bosonic matter, with no analog in the standard model. A compact object supported by the quantum mechanical uncertainty pressure of exotic scalar particles. Not fully ruled out, but no independent evidence for the required particles has ever surfaced in any laboratory or astrophysical measurement in 50 years of searching. A gravastar, a hypothesized alternative to black holes with no true event horizon, its interior filled with dark energy, and its surface a thin shell of ordinary matter. The 2022 Event Horizon Telescope image constrained but did not fully eliminate this possibility, and a handful of theorists continue to publish variants of the model that remain observationally consistent. Every alternative that has been proposed over 5 decades either collapses under its own gravity, requires new physics that has never been detected elsewhere, or fails to match at least one confirmed measurement. The only single object matching every observation, the mass, the compactness, the shadow, the stellar orbits, the flare behavior, the hidden swarm around it, is exactly what Einstein's field equations described in 1915 for a rotating black hole. Everything else fails one test or another. Every atom in every cell in your body has orbited that object dozens of times during your life. It has sat at the center of every night sky humans have ever looked up at, through every civilization, every language, every empire, every prayer. It is the invisible axis your species has always spun around, unaware. It does not know you exist, and it never will. What lies inside its event horizon, a singularity, a firewall, a doorway to a region no equation we have written yet describes. Every entry on this list sits at the center of our best tested theories, not at the edges of our ignorance. We know exactly where Sagittarius A asterisk is. We have photographed it. We have measured stars whipping around it at nearly the speed of light, and watched their orbits precess exactly as Einstein predicted a century ago. And still, the filaments, the flares, the swarm, the surviving cloud, the ancient stars, the interior of the shadow, every one of those questions remains open right next to the answers we already have. The mystery is not that our physics has failed us at the galactic center. The mystery is that our physics has taken us close enough to see, in high resolution, exactly how much we still cannot explain about the object our entire galaxy has been orbiting for 13 billion years. The universe is not confused about what it is doing at its own center. We are the ones who cannot quite look at what we have already found. If you want to see more videos like this, click the video on screen now.